Hello and welcome to the Chemistry Academy. In this video we're going to go over the SQA 2025 Higher Chemistry exam paper 1, so the multiple choice section. If you're looking for help with the answers to the 2025 paper 2, so the extended written response sections questions, you'll find me going over those in different videos that you should find in my Higher Chemistry playlists. So if we just get started with question 1. So question 1 is asking which of the following is a pure covalent bond. Now if a bond is pure covalent, it means the atoms that are bonded to each other have the same electronegativities. So we need to look up the electronegativities page in the data booklet, so you'll find those on page 12. And the first option we were given was nitrogen and bromine. So we find nitrogen, it's got electronegativity of 3. If we scroll down and find bromine, it also has an electronegativity of 3. So that is actually our answer because both of those atoms have the same electronegativities. To be sure though, it's always good to check the other options. So if we look at hydrogen and chlorine, hydrogen is 2.2, chlorine, where's the L, is 3.2, so they're different. That would be a polar covalent bond. O and H, that's definitely a polar covalent bond. We know that because hydroxyl groups always end up making molecules polar, but if we just double check, oxygen is 3.4 and hydrogen is 2.2. And then the last one, carbon bonded to iodine, carbons is 2.6 and iodine is 2.7. So although they are very close, they're not identical, so technically it's not a pure covalent bond. There is usually always one answer or two answers in the multiple choice that are quite close to both being correct, so just be very careful for those things, which is why it's always good to check all of the possible answers even if you think the first one is your correct one. So question 2, elements which are strong reducing agents, we need to work out which one of these statements is correct. So it says they undergo reduction reactions. Well, that's not true because reducing agents get oxidized. Remember, when it comes to the agents, it's like stepping into opposite land. So if you've got a reducing agent, it will get oxidized and the oxidizing agent will get reduced. So it's not going to be that one. Are found on the right hand side of the periodic table. So that means it would maybe be like a metal. So if we look at the periodic table, just to see what is on the right hand side of that, we've got things like lithium, sodium, potassium, rubidium, cesium, francium, hydrogen. To help you with this, if you then go to the electrochemical series, that gives you an idea as to what the best reducing agents are. The best reducing agents are at the top right hand corner, so we can see there's things like lithium, cesium, rubidium, potassium, all the things that are kind of on that left hand side of the periodic table. So that means that's probably our correct answer. But we will have a look at the other ones just to check. So C have low electronegativity values. If they have low electronegativity values, that means that they will easily not have much attraction for any bonding electrons. So that tends to mean that they can be easily oxidized. So that is a potential answer. And D is that they tend for God's sakes, I can't read properly. So for question 2, we're asked which of these statements are true for elements that are strong reducing agents. So for A, undergo reduction reactions, we should know that reducing agents get oxidized and oxidizing agents get reduced. So when it comes to the agents, I like to say it's like stepping into opposite land. It's always the opposite reaction that's happening to the agent. So the reducing agents will actually undergo oxidation reactions, so that means A can't be our answer. They're found on the right hand side of the periodic table. So if we have a look at the right hand side of the periodic table, that's all sort of non-metal elements like fluorine, chlorine, etc. So what we can use here as well is the electrochemical series to help us, because that kind of shows us what the best oxidizing and reducing agents are. The best reducing agents are at the top right hand side of the electrochemical series, and we can see that basically all of those things at the top right hand side are metals and hydrogen, so that would actually be things that are on the left hand side of the periodic table, so it's probably not going to be B either. Then C have low electronegativity values. Remember, electronegativity is the measure of attraction an atom has for bonding electrons. So if its electronegativity is low, it means it doesn't have a very strong attraction for any bonding electrons, which means that they can quite easily be removed, which means that they can easily be lost. So they could be easily oxidized. So that's probably going to be our correct answer. But we'll just check the last one. So that they tend to form ions by gaining electrons. So reducing agents are oxidized, which means they lose electrons. That means that they're not going to form ions by gaining electrons. They would usually lose the electrons, so it's definitely not D either. So that means C must be our correct answer. But you can see again, like there's always two that are, you're like, oh, it could be that one, but it might be the other one. So it's good to just go through all the answers every time just to make sure that you are really happy with the one that you're picking. So then for question 3, how many moles of iron 2 are required to react with 100 centimetres cubed of 0.5 moles per litre potassium permanganate solution? So this one we need to do a bit of mole calculating. So we need to know the number of moles of potassium permanganate because we can't really do anything with volumes and concentrations. We always need things in moles. So N is C times V. Don't forget to change your volume into litres, so divide by 1,000. So that means the number of moles of permanganate we have would be 0.5 times 0.1. So that would give us 0.05. if my maths is correct. So then we can take the mole ratio between the iron and the manganese or manganate. So we've got Fe2 plus is 5 moles and 1 mole of permanganate. So if we had, and that's our moles of permanganate, 0.05 moles of permanganate, then we need 5 times the amount of the iron 2, which should give us 0.25 moles. So the answer would be B. Again, if you forgot to change your volume into litres, you would have probably ended up with the answer 2.5. So as you can see, they always put answers in that if you've made a slight mistake could lead you to a correct possible answer. So the multiple choice are a bit more sneaky than they sometimes tend to come across as. So then, which of the following is the correct systematic name for the structure shown? So this molecule here is a bit of a maze, if you like. So my advice would be, if you struggle to name things from shortened structural formula, because this one has been slightly shortened, is to draw it out fully. However, if you are okay with that, then you're just wanting to try and find the longest chain of connected carbons. So we've got 1, 2, 3, 4, 5 here. 1, 2, 3, 4. Always check in L shapes. 1, 2, 3, 4, 5, 6. So we can actually get a chain of 6 if we go in that sort of snaky way. So I'll highlight those 6. So then you can see you've got 2 branches here. So we know it's going to be a dimethyl because each of those branches has 1 carbon. In terms of the numbering, we want to number from the end closest to where the double bond is. So that would be 1, 2, 3, or if we number from the other end, 1, 2, 3. So it doesn't actually matter which number we end from. So if I just number from this end, 1, 2, 3, 4, 5, 6, then we can see our branches are on carbons 3 and 4. So this would be 3,4-dimethyl hex 3-ene. Okay, and again, if you were to have missed that longest chain and named it as like a butene, you would find that the name they've given you is probably actually in one of the answers. So always make sure you check in your L shapes for your longest chains. So then question 5, which of the following is a tertiary alcohol? So the alcohol is a tertiary alcohol. It means there's a branch and the hydroxyl group on the same carbon. So you're usually looking for the 2 numbers in the name to be the same. So that quickly leads you to the answer B, because you can see the methyl branch is on carbon 2 and the hydroxyl group is also on carbon 2. Just to go through the other ones though, because the first one is a 1-ol, that makes it always primary. C is a 3-ol, so that makes it secondary, and the branch is not on the same carbon. So if the branch was on the same carbon, that would make it tertiary, but it's not, so that's just secondary. And then for D, again, it's not a 1-ol, so that means it's either secondary or tertiary. But to decide between the 2, you check the number of the branch. It's not on the same branch as the hydroxyl, the same carbon as the hydroxyl group, so that would also be a secondary. Okay, if you weren't comfortable doing that, then you can always draw them out and then have a look if you find it easier to identify from the structure. So then for question 6, which of the following is the structure of 3-ethyl hexanoic acid? There's quite a lot of naming stuff in this multiple choice, I felt. So 3-ethyl hexanoic acid. So if it's hexanoic acid, it needs to be a long chain of 6 carbons with a carboxyl group at the end. So all of these have got carboxyl groups, which doesn't help us narrow it down from the functional group. And we need to find a chain of 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So they've all got a chain of 6. The chain of 6 has to include the carboxyl group, just so you remember. So going like 1, 2, 3, 4, 5, 6, 7 down that way, that's not the longest chain because it doesn't include the functional group. So then we need an ethyl group on carbon 3. So to make this a bit easier for yourself, if you highlight your chains of 6, so your hexanoic acid chain, then you can see what the branches are. So here we've got a branch here, a branch here, branches here and branches here. So you should then be able to see in C and D that's 2 methyl branches because they're not on the same side. They're not connected to each other. They're broken apart. So that would be a dimethyl hexanoic acid. So then between A and B, we need it to be on number 3. So the one with the carbon with the carboxyl group is carbon 1. So if we number these 1, 2, 3, 1, 2, 3. So you can see that actually in B it's 2-ethyl hexanoic acid. So the answer is A because it's 3-ethyl hexanoic acid. So then hydrolysis of an ester gave an alcohol and a carboxylic acid, both of which had a gram formula mass of 60 grams. Which of the following is the structure of the ester? I think this is actually a question from a very old paper. It might be one of the higher specimens or something. I've definitely seen it in the past. Basically the trick here is that because the carboxylic acids have 1 extra oxygen in their functional group, because they've got a carboxyl group, which has got the 2 oxygens, whereas the alcohol with a hydroxyl group only has the 1 oxygen, it tends to mean that the carboxylic acid side is 1 carbon less than the alcohol side. So if you take your esters and split them in the middle of the ester link, you can then see how many carbons are on each side of like the ester. So for A, because there's the same number of carbons on both sides, they're not going to probably have the same molar mass because, like I said, the 2 oxygens, if you were to draw the molecules that were originally used to make it, the carboxyl group is going to have 1 extra oxygen, which means it's going to end up being 14 grams heavier if you take off the hydrogens that are not there. So that means you're wanting there to be more carbons on the alcohol side of the molecule to account for that 1 less oxygen. So that means the answer is most likely going to be B. Okay, you could then double check that. So we would have 2 carbons, 2 oxygens and 1, 2, 3, 4 hydrogens. 24 plus 32 plus 4 would give you 60. And then if we do the alcohol side, so there would be 3 carbons, so 3 times 12 plus 1 oxygen, 16, plus 1, 2, 3, 4, 5, 6, 7, 8 hydrogens it'll have, that's also 60. Okay, so your answer is B. But like I said, the trick is that because of the difference in the functional groups and the carboxyl group's got 1 extra oxygen, generally it means the carboxylic acid, if they were the carboxylic acid and the alcohol are to have the same mass, the carboxylic acid needs to have 1 less carbon in its chain. So then question 8, what is the change in mass when 1 mole of butanal undergoes reduction? So if we draw this out, so butanal is 1, 2, 3, 4 carbons with the carbonyl group at the end. Let's draw on the wee hydrogens. And then if it's getting reduced, that means it's being converted into butanol, the alcohol, because reduction is the opposite of oxidation. So in higher we do look more at the oxidations, but they are more frequently asking about the reductions now. So we'll just try and make sure that you know the oxidation routes backwards, because that will give you the reduction routes. So what's happened to this molecule? It's gained 2 hydrogens, which means that its mass will go up by 2 because each hydrogen atom weighs 1 gram. For question 9, 6-methyl-hept-5-ene-2-one is found in the sweat of some humans. Which of the following is the correct formula for 6-methyl-hept-5-ene-2-one? They were really loving the naming in this paper. So we're looking for a long chain of 7. And again, if you need to draw these out fully, I would advise doing that, but you can just count the carbons that are in the shortened structural formula. Anything in a bracket, remember, is a branch, that wouldn't necessarily be part of the longest chain. So we've got 1, 2, 3, 4, 5, 6. So that's not enough carbons because we need 7. 1, 2, 3, 4, 5, 6, 7. So it could potentially be that one. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So the only one we've managed to rule out with the 7 carbons is A. So then we want to look at where probably the next best thing to look at is where the carbonyl group is. So the carbonyl group is CO. Unfortunately, it's in the same place in all of them. This would be carbon 2 in all of these. But that's okay because it gives us some numbering to go with. So then if we keep continuing the numbering, we can then look to see where the branches are. 4, 5, 6, 7, 3, 4, 5, 6, 7. So we can see in D the methyl branch is on carbon 5, so that rules out D. So now we're deciding between B and C, so this is going to be down to where the double bond is. Now these are quite hard to see in shortened structural formulas sometimes, but normally you will have like a CH rather than a CH2. So you can see in B it's all CH2s, which means that's saturated, there's no double bond there. Whereas in C you've got a C rather than a CH and a CH rather than a CH2, which means that suggests there's a double bond there. So the answer, would be C for this one, because like I said, B is not actually an alkene, it's not got a double bond. But again, between those two, you would maybe want to draw them out fully, just so you can see for yourself where the gap is that the double bond would go in. It's better to be safe than sorry on these things. So then question 10, saponification is the chemical reaction between edible fats and sodium hydroxide to produce soaps. This reaction is an example of, so the actual reaction, if you were to write it in the second part of this paper 2, you would have to say alkaline hydrolysis, but the SQA like to just put hydrolysis in as their multiple choice answer, which personally I find a bit hypocritical, but so it would be an example of hydrolysis, but if you were naming it specifically alkaline hydrolysis. Question 11, an emulsion can be formed by shaking vegetable oil and water with an emulsifier. The emulsion formed, the fatty acid chains of the emulsifier are. So we should know that fatty acid chains are hydrocarbon based, so that means they are hydrophobic. They don't like water. So that means they would be hydrophobic and they would dissolve in the vegetable oil droplets, okay, because they avoid the water. So that would be D. Question 12, which of the following is a terpene? So terpenes are made up of isoprene units, and isoprene units contain 5 carbons. So if something is made up of isoprene units, then it should have multiples of 5 carbons. So that leaves the only answer to be B, because that's the only one that you can divide evenly, the number of carbons, by 5 to get a whole number. So then for question 13, an investigation was carried out to determine the effect of changing temperature on the rate of a reaction. The results from the investigation are shown in the graph. Use the graph to determine the temperature rise in degrees Celsius required to double the rate of reaction. So you really just have to pick 2 rates here, one of which is double the other. So I'm just going to pick 0.2 and 0.4. So at 0.2, these graphs are so hard to read sometimes. The temperature was 44, and then 0.4, the temperature was 56. So that means from 44 to 56, that was an increase of 12 degrees. So that's how much of an increase you need to double the rate. Even if you were to pick, say, 0.4 and 0.04 and 0.08, you should still get that difference of 12 degrees. Or if you picked 0.06 and 0.12, it should all come out as 12. So then for question 14, which of the following diagrams shows the distribution of kinetic energies for the molecules of a reaction when the temperature of the reaction is increased from T1 to T2? So if you're increasing the temperature, it means more of the molecules have a higher kinetic energy. So if you think of these diagrams as piles of sand, you're going to be shifting your pile of sand over and to the right. So it's kind of like if you imagine it as a big sandcastle, it's like you're pushing the sandcastle over and sort of smoothing it out a bit to the right hand side. So T1 was where it was the lower temperature, so we can see in T2 in this one, the pile of sand has kind of been pushed over. In B, the pile of sand is like you've removed sand from it. It's gotten much lower, but it's not actually been pushed over. So it's like you've just taken a scoop of sand and chucked it away. In C, it has been moved, but you've clearly added more sand to it as well because the peak's actually higher. So that's like adding more molecules, so that doesn't count. And then in D, again, you've just added more molecules because now the sandcastle's just a bit bigger. It's not actually been pushed over and moved. So that means the answer is A. So it's very important in these diagrams that the number of molecules doesn't change unless something in the question has told you you've added more of the reactant or something. So if you're just changing the temperature, you're going to have the same amount of sand, you're just going to be moving it. So if you are increasing the temperature, the pile of sand is going to be like knocked over and pushed over to the right. If you're decreasing the temperature, it's like pushing your pile of sand back up to the left hand side. Oops. So question 15, some energy values associated with a chemical reaction are shown in the table. What's the enthalpy change for the forward reaction? So you've got the activation energies of both the reactions here. So sometimes it's quite helpful to like sketch it out. So for the forward reaction, you're going up 165. 165. So 165. And for the reverse reaction, you're going up 179. So that's going to be a bit higher. So that means this line will be a bit lower. So I'll just do that there. So then for the enthalpy change, you can see then you need to find the difference here. So you'd want to take 165 away from 179. So that gives you a difference of 14. And it would be minus 14 because the energy is dropping for the forward reaction because you're starting at a higher level. So if you think of it as a bank balance, it's like you've got more money in your bank here than you do at the end. So it'd be minus 14. It's the plus minus bit and the enthalpy change that usually catches most people out. So thinking of it like a bank balance does help. It just makes it a bit more relatable, I think. So question 16, the equation for the reaction at equilibrium is shown. Which of the following conditions will favour the formation of B? So the reaction is exothermic, the forward one. We can see that from this information here. So remember, when it comes to equilibrium and temperature, if you remember Nintendo, like Nintendo without the N at the front, then that means that an increase in temperature will favour an endothermic reaction. So if we've got an exothermic reaction, then we're going to want a lower temperature. So our reaction temperature we want to be low, so that rules out C and A. And then for the activation energy of the forward reaction, if the activation energy is high, it means the reaction's harder to get to happen. You need to like heat it more and things, provide it with more energy. So if you have a lower activation energy, then that will mean the reaction's more likely to happen. So we would want for the forward reaction a low activation energy as well. Okay, so it should be low temperature because it's exothermic, and a low activation energy would be better as well. So then 17, for the reaction pathway, what's the relationships between A, B and C? So C is the product of the formula, as the mathematicians would say. That means that's the route we're trying to take. So we're trying to work out what the energy change here would be. So imagine that's a road that's been closed. You're trying to get from the start to the finish. I'll put S and F actually. But you can't go that way anymore because that road's closed. So we have to go along this road instead, but we're going the opposite direction of that street, which means that becomes minus A. And then we're going along this road, and that's the same direction as the arrow's already going, so that's positive B. So it would be minus A plus B is what would give us C. Then question 18, according to Hess's law, which row in the table shows how equations 1 and 2 should be manipulated to calculate the enthalpy change for equation 3. So equation 3 then is our target. So that's our target equation. So if I always go from the target equation to the sub-equation, so in the target equation I need 2CH4. CH4 is in equation 1, which means I need to times that by 2 to get 2 of them. Then if I go along, oxygen's there next, but oxygen's in both reactions, so then I'll just skip that to make my life a bit easier and hope that it'll all work out in the end. Then we need CO, 2CO, so that's in equation 2, but it's on the wrong side. So I've got the correct number of moles, but it's on the wrong side, so that means I need to reverse this one. And then the water is in this equation, which I need 4 moles of it, and it's only got 2, so I'm timesing it by 2, so that's going to end up giving me 4. So that means that equation 1 should be multiplied by 2, and B should be reversed. So that would, or equation 2 should be reversed, so that gives us the answer B. Which of the following is the correct statement about the catalyst in a reaction? So the catalyst doesn't increase the activation energy, it actually decreases it, so that's not true. It decreases the kinetic energy of the reactant particles. The only thing that changes the amount of kinetic energy that the particles have is changing the temperature, so that's not going to be the answer either. It shifts the equilibrium to the right. We should know that catalysts don't change equilibrium because they increase the rate of the forward and the backwards reaction equally, so that's not correct answer either. And it has no effect on enthalpy change. That's correct. The only thing that will change the enthalpy change of a reaction is changing the reaction and not doing that reaction anymore. So that must be D. Question 20, a two-step reaction is shown below. Step 1 gave a yield of 50%. The overall yield of product C was 40%. The yield for step 2 would be... These ones are really tricky. They've had one before a few years ago. It was the first time they put it in. It kind of threw everyone a bit of a curveball. So, and this one's even slightly different. Again, it's probably harder actually that they've done this. So picking a number to start with really helps here. So I would also advise picking 100 because it's like 100%. So you start off with 100 and then you end up going to 50. And then it says at the end, because 50% of 100 is 50, and then at the end it says that you've ended up with 40%, which means that if we started with 100 molecules, we've only got 40 at the end. So we need to basically work out what percentage of 40, what percentage 40 is of 50. So you need to do 40 over 50 times 100, and that'll work out what percentage 40 is of 50. So I think it's going to be 90%, but or 80% maybe. 40 divided by 50 times 1. Oh, 80%, yeah. Okay, so this is, yeah, a bit more numeracy, math stuff, a knowledge of percentages more than chemistry, to be honest. But yeah, starting off with 100 when it comes to these sorts of questions, like I said, I've only seen it once before, and it did throw everyone a curveball that year as well. That's how you want to kind of probably approach it. Just pick the number, like as 100, and just work out percentages of 100. So then for 21, a mixture of aluminium phosphate and aluminium sulfate is known to contain 5 moles of aluminium ions and 1 mole of phosphate ions. How many moles of sulfate ions are present? So for these questions, we need to know the chemical formulas of the ionic substances. So we've got to do a bit of SVSDF. So aluminium's Al. Phosphate you'll find on page, it's not on page 8 in this one. It's on page 8 in the National 5 one. And this one I think it's on like page 9. Yeah, there we go. So there's phosphate. Oh, here, PO4 3 minus. So that means its valency is 3 because it's 3 minus. Aluminium is in group 3, so its valency will also be 3. So if we swap them over, that becomes 3 and 3. That simplifies to 1 and 1, so that'll just be Al PO4, so 1 mole to 1 mole. So we don't actually need the final formula written really, we just need the mole ratio. So then for aluminium sulfate, so sulfate is SO4 2 minus, so that means that it's got a valency of 2 because its charge is 2 minus. Aluminium is valency is 3 because it's in group 3. Oops, sorry. So then we swap them over, that's 2 and 3, which means it's a 2 to 3 ratio of those ions. So it says you've got 5 moles of aluminium ions, so that's not that helpful at the moment because that's in both compounds, so I'll just write that in the middle. But it tells you there's 1 mole of phosphate ions, so that's a bit more helpful. So we know we've got 1 mole here, which means we must have 1 mole here. If we've got 5 moles of aluminium in total, that means we must have 4 moles over in this compound, which then, based on the 2 to 3 ratio, we divide by 2 times by 3, so that should mean that there's 6 moles of sulfate ions present. Okay, so that's how you want to tackle those ones. I'll actually write the moles here after the numbers that we've worked out because it makes it a little less confusing as to what's an actual number of moles and what's a ratio. So then, the electron affinity of an element is the energy change when 1 mole of gaseous atoms combines with 1 mole of electrons to form 1 mole of gaseous ions. Which of the following equations represents the electron affinity of chlorine? So this is a bit of problem solving. You've got to read what electron affinity is and then apply that to what that would look like in an equation. So you've got 1 mole of gaseous atoms. That rules out B and C because they're not atoms, they're molecules of chlorine. And then it's combining with 1 mole of electrons. So the only answer where it's actually combining with a mole of electrons is A, because in D the mole of electrons are actually being lost. So that would be ionization. So then, which of the following equilibrium exists in bromine solution? 23. The following equilibrium exists in bromine solution. The red colour of the solution would fade on adding a few drops of a concentrated solution of what? So we're looking for, if the red colour's fading, the equilibrium shifting to the right because that's when it's becoming colourless. So if we look at what we've actually added, we're adding H.
Oh.
I'm making a video, can you please just give me 10 minutes, thank you.
And what's the door thing?
So that means we're adding H plus and Cl minus. In this one, for B, we're adding K plus and Br minus. For C, we've got Ag plus and NO3 minus. And then in D, we've got Na plus and the OBr minus. If you're not sure what some of the ions are, if they look a bit unusual, then just have a look at the reaction because normally they're in there somewhere you can see. So now that we've got the ions, we can see what we're actually adding. So if we're adding HCl, H plus ions are in the reaction, so that means we're adding more of those, so the equilibrium is going to shift to remove them, so that will actually shift it to the left and it would actually appear more red. So it's not going to be that. The Cl minus ions, they're not in the reaction and they don't ever form precipitates or anything, so or remove any other ions usually, so they're not going to cause an effect. Then for B, potassium ions aren't in it, and again, they're ions that don't tend to really affect the concentration of any other ions. And we've got Br minus, so we're adding more of this, which means the equilibrium is going to shift to the left to remove it. So that means that that's going to make it more red. So then for C, we've not got any silver ions or nitrite ions in there. So we'll just skip to the next one for now. Sodium is not there. OBr minus is there. If we're adding more of that, that's going to shift it to the left to remove it. So that's not going to be our answer either, because that's going to make it more red. So that means it leaves us with our answer being C, but at this point in time, we're maybe not sure why the answer is C. So what we want to do is look at how some of these ions might be interfering with things. So nitrate, if we go and have a look, so this is where we want to have a look at precipitates. So if we go to the precipitates table, nitrate doesn't form anything that's insoluble, so that's not going to have caused any difference. But we've also got silver ions, so if we have a look, silver does cause insoluble substances, and with bromide ions, which we've got bromide ions in our reaction. So that means the silver ions are going to remove the bromide ions. And then because the bromide ions are being removed, that is going to shift the equilibrium to the right to regenerate them. Okay, because if there's no bromide ions there, then it means the reverse reaction can't happen as quickly because they're a reactant in the reverse reaction. So that's why our answer is C, is because the silver ions are removing the bromide ions from the equilibrium, which then slows down the reverse reaction. So not an obvious one in that one. They've not had the precipitate forming thing in a while. Normally it would be like hydroxide ions removing the hydrogen ions, so they've switched this up a bit. But again, this was one from an old exam, like a very old higher exam, this question. This is why it pays to do past papers, because quite often some historical questions can be reused. So when carrying out a titration to determine the mass of vitamin C in a tablet, which of the following will not help determine the end point of the titration accurately? So accurately is the key word here. There's one of these things that only helps with precision, and this is worth remembering. The thing that only helps with precision is using the white tile, because even though you've got white tile underneath your conical flask helping you see the end point more clearly, like as in the colour change, you could still have all these other things that end up causing it to be inaccurate. Like you don't add drop-wise towards the end point, your conical flask wasn't dry, so that's altered the concentration of your solution. Swirling the flask helps with the accuracy because it encourages the molecules to continue reacting with each other. So yeah, it's the white tile only helps with precision, so that's helping you get your results close to each other. To get close to the accurate, true result, which is what accuracy is, that's when you need to do all these other things. And like reading the burette from the bottom of the meniscus. I've got a video on titrations, practicals, that goes through some accuracy, precision stuff, so you can go and have a watch of that if you need that info. So then question 25, what volume of solution was added from the burette? So the diagrams show the burette at the start and end of the titration. So what have they added? So from at the start there was 12.1, 2, 3, 4, 5. So we read from the bottom of the meniscus. So that's 12.5 centimetres cubed. And then at the end there was 24.123. So all we really need to do is take those away from each other. So 24.3 minus 12.5, oops, that gives you 11.8. So A. And that was the last question. This one's a bit tricky because I think people maybe forget that you're always reading a burette from the top down, and just also again remembering that you always read from the bottom of the meniscus. So I hope that was helpful. Like I said, if you're looking for help with the paper too, then you can go and check out my other videos at my Higher Chemistry playlist. But don't forget to subscribe and follow me on TikTok for more help preparing for your chemistry exam in the future. And thanks for joining. I'll see you again soon.